For this week, we're going to discuss number theory. So, number theory, it means we are going to discuss the different properties of an integers. So, for example, divisibility, being a prime number, and others. Okay, and also we're going to discuss in this week the different representation of our numbers. So we have integers, we have binary hexadecimal, and also we're going to discuss the old ways of representing our numbers. Okay, so so the summary for this chapter would be, so we're going to start with divisibility and modular arithmetic, followed by integer representation and algorithm, followed by prime's greatest common divisor. Fourth topic will be solving and congruences, and last topic will be applications of congruences. So let's start with our first topic, divisibility and modular arithmetic. Okay. So just a summary about this section, we're going to discuss what is division algorithm, and what is modular arithmetic. So let's define first what is division. So based on our book, division definition. If A and B are integers with A is not equal to 0, then A divides B. If there exists an integer C such that B is equal to AC. So basically, the division means here, okay, a number is a divisible, when we divide a number, when we divide it to another number, it will give us an integer or a whole number. So it means a number is divisible to another number. Okay, so that's division. Okay, so the relations between A and B. So if A divides B and the result is a whole number, we could say that A is a factor of B, or A is the divisor of B, since it gives us a whole number or an integer as a result. Okay, and if you're going to refer to B, so we could say that B is a multiple of A. Okay, so we're going to multiply something in A that will yield to B. So that's the meaning of multiple. Okay, so the notation to define that a number divides another number, we use a pipeline. Okay, so A is your divisor, B is your dividend. So A divides B. Okay, so it means A is divisible by B. B is divisible by A rather. Okay, so when we read this, A divides B. Okay, and if A divides B, then B divided by A is an integer. Again, it should be a whole number so that we could say that A is a factor of B. Okay, and in case if it's not an integer, the result of the division is not an integer, this is how we're going to write it. We just put a slash on the pipeline. So it means A does not divide B. So the result means it's not an integer. Okay? It's not an integer. That's the meaning of does not divide. Okay? So let's have an example. Let's determine whether 3 divides 7 and whether 3 divides 12. So let's start with 3 divides 7. So what is the result? 7 divided by 3, the result, the quotient, is not an integer. Therefore, 3 does not divide 7. Okay, since the result is not an integer. Okay, let's have 3 divides 12. So 12 divided by 3, what is the result? It's a whole number, it's an integer, which is 4. Therefore, we could say that 3 divides 12. 3 is a factor of 12. 12 is a multiple of 3. Okay, so that's the definition of of division. So let's move on with the next slide. So let's discuss the different properties of divisibility. So it is stated in theorem number 1. So we have let A, B, and C be integers where A is not equal to 0, since A is our divisor, so it should not be equal to 0. Okay, so form 1. If A divides B and A divides C, then A divides B plus C. So if we have two numbers and it is, okay, and it is, what do you call it? And it is divided by A. So when we add these two numbers, still A can divide it. So that's the meaning of the form 1. Form 2, if A divides B, then A divides B m for all integers m. So when we introduce a new value and multiply it to B, to our dividend, the result is still A is a factor of that product. Okay, so there's no change. It will not yield to a not does not divide. Okay, still A is a factor. Okay, when we introduce an integer to our dividend, A is still a factor. Okay, form 3. If A divides B and B divides C, then A divides C. So we could say that here B is a factor of C and A is a factor of B. Since we have a common values here, we could say that since B is based on A, we could say that C is also based on A. So A is a factor of C, okay, based on the relationship through B. Okay, so that's why the result is A divides C. Okay, just to prove that form 1 is correct, it's right. So let's have this. Okay, so suppose A divides B and A divides C. So based on division division definition, there is a value when we multiply to our divisor, it will yield to our dividend. So here, so S will be multiplied to A to yield B. Here, we multiply A by T to yield C. Okay, so B is equal to AS and C is equal to AT. Okay, so these are our two equations. So based on form 1, we have B plus C. So let's substitute AS and AT to B plus C. So it will be rewritten as AS plus AT. We have a common variable or common term, which is A. So let's factor it out. So it means we have A times S plus T. And what is this form? A times any value is equal to B plus C. So this is definition of, or the format of division. Am I right? Okay. Any value multiplied to your factor will yield to this dividend, which is B plus C. So therefore, it's correct. Okay. So based on theorem number 1, we have a corollary. Okay. So if A, B, and C are integers where A is not equal to 0, such that, by the way, corollary is an extended version of the theorem 1. So this is based on theorem number 1. Okay. So A divides B, A divides C, then A divides MB plus NC whenever M and N are integers. So when we introduce an integer and multiply it to B and C, still A is a factor of the sum. of MB plus NC. Okay, so again, this is just an extended version of theorem number 1. So for your first assignment, prove that form 2 and form 3, okay, is correct. Again, first assignment, prove that theorem number 1, form 2, and form 3 are correct. So you could base your solution based on my proving for form 1. Okay, now let's continue. So let's discuss division algorithm. So division algorithm give us an idea how we do the division. We have a formula. Okay, so for division algorithm, if A is an integer and D a positive integer, then there are unique integers Q and R with 0 less than or equal to R less than to D, such that A is equal to DQ plus R. So for division algorithm, this is the working formula. A is equal to DQ plus R, wherein D is the divisor, A is the dividend, Q is a quotient, R is a remainder. So in this division algorithm, D is always positive based on this definition, okay? And A is an integer, and R, don't forget, this is the range. It should be less than the divisor, but not less than 0. So the minimum value will be 0. 0 to less than the divisor. Okay, and then R is the remainder. Okay, so that will be division algorithm. So we have two functions here. We have div or div, mod or mod. So if you're going to use div, the result will be the quotient. So A div D means the result will be Q, which is the quotient. And if we have A mod D, it means the output or the result is the remainder. Okay, so let's use this equation, this on this definition on how to do division. Okay, so let's have this first example. What are the quotient and remainder when 101 is divided by 11? So using A is equal to DQ plus R, 101 is A, 11 is D. So what will be the value of Q and R that would, okay, that would satisfy this equation? Okay, so we're going to use A div D. So we have 9. Then 101 mod 11, we have 2. So that will be the result. Quotient is 9, R is 2. But how about negative 11 is divided by 3? So we're going to divide 3 to negative 11. So what will be the result of D and R? Okay. So this will be the result. Negative 11 division by 3, it's negative 4. Why negative 4? Why not negative 3? Okay, why? Because if we're going to use the result is negative 3 here, what will be the remainder? It will be negative 2, which is incorrect based on our definition of division algorithm. It should be between 0 to less than your divisor. It should always be positive or 0. So therefore, we could not have a negative 2. So that's why we need to adjust our quotient. So instead of negative 3, we're going to make it negative 4. So that's why when we multiply negative 4 to 3, we have negative 12. and then the result is negative 11 as your divisor, I mean as your dividend. So what will be the number to be added to negative 12 to give us negative 11? It's 1. Okay, so that will be the result. Negative 4 times 3 plus 1 will yield to negative 11. Okay, so medyo tricky ang kapag negative yung ating dividend. Okay, we need to check if the remainder is positive. It should be always positive, okay, for the division algorithm. So if it will be negative, so we need to adjust the quotient to give us a positive remainder. Okay, so based on this example, we did it. Okay, so more example of this on the next video lecture. Okay. Now, let's move on with congruence relation. So definition. If A and B are integers and M is positive integer, then A is congruent to B modulo M if M divides A minus B. Okay, so basically, when we subtract a certain value, okay, to another number, and when we divide it by M, the result should be an integer. Okay, so it means it is congruent. Okay, so A is congruent to B modulo M. Okay, so when we subtract a value and when we do modulo, okay, modulo M, when we divide M to that, to the result of A minus B, okay, and it's an integer, so it means they have a congruence relation. Okay, so the denotation will be for the congruence relation A, 3 lines, B mod M. So when we read this, so it will be read as A is congruent to B modulo M. Okay, again, modulo M, this M is your factor when we subtract factor of the result of A minus B. Okay, so that's the meaning of the congruence relation. And in case the result, okay, if not, it doesn't conform with the congruence relation, this will be our notation. We're just going to put a slash on the 3 lines. Okay, so it means A is not congruent to B modulo M. So it means when we subtract B to A, okay, and then divide M to the result of A minus B, it didn't yield an integer. So it means there's no congruence relation. Okay, so let's have an example. Determine whether 17 is congruent to 5 modulo 6 and whether 24 and 14 are congruent modulo 6. Okay. So let's answer the first. 17 is congruent to 5 modulo 6. So we're going to subtract, okay, 5 to 17. So we have 12. And then we divide 6. So is it a whole number? Is it an integer? Yes. So therefore, okay, so 17 is congruent to 5 modulo 6. Okay, since when we subtract 5 to 17 and then we divide 6, it gives us an integer. So therefore, we have congruence relation. Okay, another problem. So in 24 and 14, congruent modulo 6. Okay, so we subtract 14 to 24, the result is 10. And when we divide it by 6, the result is not an integer. Therefore, we don't have a congruence relation. Okay, so that's why we have a slash in our symbol. So 24, okay, is not congruent to 14 mod 6. Okay, so that's congruence relation. So more on congruences, theorem number 4. So basically, this is related to division definition. Okay, theorem number 4. Let m be a positive integer. The integers a and b are congruent modulo m if and only if there is an integer k such that a is equal to b plus km. Okay, so it means that, okay, so when there is an integer, when we multiply to m and add to b, it will yield a. Okay, just for proving. So again, a is congruent to b mod m. We could rewrite this as, okay, based on our definition, based on the congruence relation, okay, we could rewrite this format, this equation as this. Okay, since we are testing the divisibility of m to a minus b. Okay, so this is division definition. Okay, so m divides a minus b. And based on the definition, okay, so we have a certain value, okay, so this, it will be divisible if we have a certain integer. When we multiply to m, it will yield the result of a minus b, okay, based on the division definition. And then by manipulating this, transferring b to the right side, we have a is equal to b plus km, which is this. Okay. And also, just to prove it the other way, we have this equation a plus b km. So transfer b to the left side. So we have a minus b km. And based on definition of, again, divisibility or division, so any integer multiplied to m, if there's a value when multiplied to m, is equivalent to a certain integer. Therefore, m divides that certain value, which is a minus b. Okay, so that's how we prove theorem number 4. Now, so don't forget this mod m is different from this mod m because this mod m refers to relationship, congruency, while mod m, okay, so it is a function that determines the remainder. So that's the difference between the two. Even though we are using same words, but notation is different, so therefore it means different. Okay, but there is a relationship between the congruency and mod m. So we have theorem number 3. Let a and b integers and let m be a positive integer. Then a is congruent to b mod m if and only if a mod m is equal to b mod m. Okay? So it means when we divide m to a and m to b, it will yield the same result, same integer. So we could say that they are congruent. Okay? So that's another property of congruence relationship. Okay? Now, congruences of sum and products, theorem number 5. So let m be a positive integer. If a is congruent to b mod m and c is congruent to d mod m, then we have a plus c congruent to B plus D mod M, and so we could do the multiplication of AC is equal to BD mod M. Okay, so basically these two equation is divisible by M. So if we have this scenario, we could add A and C, B and D, still M is the factor, or yeah, it's the result of this sum will be divisible by M. Okay, addition, sum, or product. Okay, just to prove that this is correct. Okay, so again, we have these two equations, two relationship, and based on theorem number 4, we could rewrite these two relationship as B is equal to A plus M, wherein S is any integer when we multiply to M and add to A will yield to B. Same as with this, T is an integer when we multiply to M and add to C, it will give us D. Okay, now, so we have B plus D. Okay, so substitute this equation to B and D, then manipulate. So we have, so plus, plus, plus. So we're going to associate SM with TM since they have the same factor, which is M, factor it out. Okay, so we have A plus C plus M is equal to S plus T. Okay, and what is this form? Based on theorem number 4, the same as this. Okay, so therefore, the first form is valid. Okay, same as with multiplication. So BD substitute. So, and then when we manipulate it, this will be the result. Okay. So again, it conforms theorem number form. Okay, any integer multiplied to M. There is an existing integer that when we multiply to M, add to an integer will result to this. We have that. So it conforms with theorem number 4. Okay, now let's have an example. 7 is congruent to mod 5 and 11 is congruent to 1 mod 5. Tama ba? 7 minus 2 is 5. Mod 5, result is 1. 11 minus 1 is 10. Mod 5, we have 2. So equation is correct. So now let's apply theorem number 5. Okay, so we're going to add 7 plus 11. Okay, so we have 18. And then for the modulo, and for the B plus D, so we have 2 plus 1 is 3. Okay, so 2 plus 1 plus 3. Then subtract 3 to 18, we have 15. Divide by 5, the result is 3. So therefore, they are congruent. Okay, so for multiplication, so 7 times 11, we have 77 is equal to 2 times 1. Okay, so we have 2 minus, subtract 2 to 77, we have 75. Then we divided by 5. Is the result an integer? Yes. So therefore, they are congruent. Okay, so that's theorem number 5. Okay, so we also have algebraic multiplication of congruence. So if A is congruent to B mod M, holds then C times A is equal to C times B mod M, where C is any integer hold by theorem number 5, okay, with D is equal to C, okay? But don't forget, for the division, it's not applicable, okay? Now, computing the mod M function of products and sum. So if we have this, so A plus B mod M, okay, could be rewritten as A mod M plus B mod M mod M. Okay, so basically we just distribute mod M to each and we retain one mod M. Okay, AB mod M, A mod M, B mod M, and then mod M. So this is how we evaluate this equation. Okay, and again, this is based on theorem number 5. This is an extended version of theorem number 5. Okay, now let's move on with arithmetic modulo M. Let Zm be the set for non-negative less than M. Okay, so an integer, positive integer, Zm, Z sub M is equal to 0 to M minus 1. The operation plus M is defined as A plus MB is equal to A plus B mod M. And for multiplication, so it's almost the same notation, but instead of plus, it will be product. So A times M, B is equal to A times B mod M. This is how we evaluate this equation. Okay, so for example, we have 7 plus modulo M 11, 9. Okay, and 7 times 11 modulo 11, 9. Okay, using the definition above, so we're going to add first 7 plus 9, and then the result will be divided by 11. Okay, and then the result is 5. Okay, that's the meaning of arithmetic modulo M. And here, 7 times 9 modulo 11, and then when we divide, the remainder is 8. Okay, so that's arithmetic modulo M. And these are some of the operation or properties that we could apply, or rules that we could apply in arithmetic modulo M. So closure, if A and B belong to Z sub M, then A sub M B and A sub M B belongs to ZM. So basically it's just a definition. Then associativity, if A, B, C and belongs to ZM, Z sub M, then A plus modulo B plus modulo C is equal to A plus modulo B plus M modulo C. And A multiplied to modulo B times modulo C is equal to A modulo B times modulo C. And for commutative, you could change or alter the organization. And for identity, okay, so anything add to 0 is still A, and anything multiplied to 1 is still the same. Okay, A plus 0, so A plus modulo 0 is still A modulo 1 is still A. Okay, A times modulo 1 is equal to A. Okay, and some additional rules about arithmetic modulo. So if we have this, we're in the modulo, it's inside this. So, and then we subtract A. So the result will be 0. And in case we have this distributivity, okay, we want to distribute, okay, we want to separate B plus B to M to modulo C, okay, so this will be the format. So A, okay, first A M B, then A M C, and then Don't forget the M. Okay, so inside the modulo, we're going to distribute. Okay, same as here. So it will be AMC, and then since we have M, so we have M here. Okay, and we're not going to discard multiplicative inverse since not all the time we have multiplicative inverse. Okay, so on the next video lecture, we're going to discuss integer representation and algorithm. Okay, and for samples about modulo will be on another video lecture. Okay, so if you have any question, okay, so kindly send me a message. Thank you for listening. See you in the next video lecture.